Hi! In this video, I'm going to show you how to construct an axial force, shear force, and a bending moment diagrams in two different methods. I'm going to do it in the first, which is the long way on my previous video, and in the faster way. So, the first things first, to draw the reactions at our supports. So I have a vertical support, call this as VB, and a vertical and a horizontal reaction at A, VA, and also HA. The sign convention, positive upwards, to the right, a clockwise moment. My three equilibrium equations will be sigma F to the x direction or to the horizontal direction equals to 0. So I'll have a positive HA equals to 2.5 cosine of alpha. Sigma forces to the vertical directions equal to 0. I'll have positive VA and a positive VB minus 2.5 sine of alpha minus 2 times 5, the uniformly distributed load, and then 1 times 2 equals to 0. And then the last I'm going to take is a sigma moment at a certain point equals to 0. I'm taking sigma moment at A equals to 0. So I've shown you the way to calculate a moment at a certain point on the previous video, so go check them out. Since I got VB, I can calculate VA. So the faster way to construct an V and M diagram is to see the forces and the moments at every part of the beam. So I'm going to have like this part and this part and this part right here. We're going to make the N diagram first. If you can see at part 1, there's no actual force. So the actual force on part 1 will be 0. And then on part 2, there's HA working to the right. So I'll have a minus 1.5 tons working from A. And then it's going to be cancelled out by this. Why is it negative? Because if you're like closing your beam like this, then you're seeing like the left side of the beam, you're going to see that HA is going inside the beam. It's going to give your beam compression. Now onto the shear force. So at part 1, we have uniformly distributed load of 1 ton per meter along the 2 meter part of the beam. So it's going to be 0 from here. And since the UDL is going upwards, so it'll go 1 times 2, which is 2 tons. And then it's going to go upwards since it has a kick of VA. So I'm going to have like a 4.2 right there due to VA. Then it's going to have a downwards reaction from the UDL, which is 2 tons per meter along the 5 meter part of the beam. So it's going to be 4.2 minus 2 times 5. And then it's going to have a kick of an upwards VB of 7.8 tons. At part 3, there's no load, so it's going to be constant. And then there's going to be a downwards of 2.5 sine of alpha, which is also 2. So it goes like this. Okay. So now on to the M diagram. Do not forget that we actually have a maximum moment right here, and we're going to calculate that maximum moment with using what I call the triangular rule. So for making the moment diagram, it's going to have 0 moments at every end since it's not a fixed end. So at point A, if you're looking from the left side of the beam, which is this part right here, it's going to have a positive moment of 1 times 2 times the distance. So I'll have a positive 2 centimeters. We're going to see at point B. To make it easier, we're going to see it from the right side of the beam. So I'm going to close this part right here, and what I have is this minus 2.5 times sine of alpha times the distance, which is 1 ton meter at B. So it's going to be a negative bending moment. So now we're going to calculate the maximum moment due to the extreme shear force. So using my triangular rule of this yellow shaded triangle right there, I'll get that. And we're going to calculate x. So the maximum moment will occur at 2 meters plus 2.1 meters. So we're going to calculate the moment at 4.1 meters from the left side of the beam. I'm sorry because the paper just won't fit. So here we go. The N diagram, the D diagram, or the V diagram, and the bending moment diagram of a simply supported beam.